The telegram arrived at the Detroit office on a gray November morning, 6 weeks before Pearl Harbor would drag America into a war it desperately hoped to avoid. Inside, 3 words shattered the illusion of distance. Britain needs tanks. What the telegram didn't say, what everyone in Washington already knew, was that Britain didn't just need tanks. Britain was bleeding tanks faster than any nation on Earth could build them. William Signius Knudsen stood in the cavernous Chrysler production facility, his Danish accent still thick despite 4 decades in America, staring at the skeletal frame of what the Army called a medium tank. Around him, skilled craftsmen moved like surgeons, hand-fitting each plate, custom grinding each joint. Beautiful work, meticulous work, impossibly slow work. Each tie. Tank took approximately 3 months to complete, assembled by hand as though building a cathedral rather than a weapon. The United States produced roughly 300 tanks per year, a number that would barely replace British losses in a single bad month. Knudsen had built his reputation transforming Ford's production systems, then risen to lead General Motors. President Roosevelt had personally summoned him to Washington, asking him to chair the newly formed Office of Production Management. Now, at 62, the engineer faced a problem that made civilian automobile production look like child's play. Tanks weren't cars. Very military experts said so. Tanks required precision tolerances, specialized armor plate, complex transmission systems, and weapons integration that demanded individual craftsmanship. The very idea of mass production seemed absurd, but Knudsen had heard impossible before. The British experience told a grim story. According to manufacturing reports from the Ministry of Supply, referenced in David Edgerton's Britain's War Machine, British factories struggled to produce 1,500 tanks annually despite total mobilization. The Germans, with their vaunt at industrial efficiency, managed perhaps double that number. Meanwhile, Hitler's panzer divisions were cutting through Soviet defenses, destroying thousands of tanks in weeks. The mathematics were brutal. If America entered this war, current production methods would be utterly inadequate. The Army brass didn't help matters. General Jacob Devers, chief of the armored force, insisted tanks required specialized facilities and specialized workers. His engineers presented Knudsen with specifications that seemed designed to prevent mass production. Custom-cast hulls, hand-fitted turret rings, individually calibrated gun sights. Each component carried tolerances measured in thousandths of inches. One colonel actually argued that assembly line methods would compromise battlefield reliability, as if German shells cared about manufacturing philosophy. Knudsen walked the factory floor, his engineer's eye cataloging inefficiencies. Here, 3 men spent 2 days fitting a transmission housing because each tank's frame dimensions varied slightly. There, specialists hand-riveted armor plates in sequences that couldn't be standardized. Overhead cranes moved glacially, positioning components that required precise manual alignment. The whole operation resembled a luxury car workshop, not a wartime production facility. The problem wasn't the workers. American industrial labor was the finest in the world. The problem was the process itself, built on European craft traditions that had dominated weapons manufacturing for centuries. Knudsen recognized the challenge immediately. He needed to convince both military leadership and manufacturing engineers to abandon centuries of doctrine and embrace something that had never been attempted at this scale. His impossible blueprint was already forming, though even he couldn't yet see how revolutionary and controversial it would become. Early 1942. 3 months after Pearl Harbor, Knudsen presented his proposal to a conference room full of skeptical generals at the War Department. The plan looked insane on paper. Transform tank production using assembly line principles, standardize every component, and implement interchangeable parts across entire production runs. The target? 500 tanks per month from a single facility, a number that exceeded America's entire annual output just 1 year earlier. Colonel James Chibber, the Army's chief ordnance officer, spoke first. "Mr. Knudsen, tanks are not Chevrolets. You cannot simply stamp out armor plate and expect it to withstand 88mm shells." His tone carried the weariness of a professional addressing an amateur. Around the table, heads nodded. These men had spent careers managing weapons production through traditional methods. They understood metallurgy, ballistics, and battlefield requirements. What did a car manufacturer know about warfare? Knudsen expected this resistance. He'd brought blueprints, production flowcharts, and something else. Photographs from the Chrysler Tank Arsenal construction site in Warren, Michigan. The facility, barely broken ground, would become the largest tank production complex in the world. But none of that mattered if he couldn't change how these men thought about manufacturing. "Gentlemen," Knudsen began, his Danish accent emphasizing each word. "You are correct that tanks are not cars, but production is production. The principles do not change." He unrolled detailed specifications for the M3 medium tank, soon to be replaced by the M4 Sherman. Every inefficiency in your current system comes from variation. Each tank is slightly different, so nothing is interchangeable. Workers must fit parts individually. You cannot train new labor because every assembly requires judgment. You have created a system that cannot scale. The real heresy came next. Knudsen proposed completely redesigning the Sherman tank, not for battlefield performance, but for manufacturing efficiency. Curved armor plates would become flat panels that could be stamped rather than formed. Complex castings would be simplified, even if it meant slightly thicker armor to maintain protection. Turret rings would be standardized to precise tolerances, so any turret would fit any hull. Most controversially, he wanted to reduce the number of unique parts from over 20,000 to fewer than 10,000 through standardization and modular design. General Devers interrupted. "You're talking about compromising combat effectiveness for production convenience. Every change you propose makes the tank heavier, less maneuverable, potentially less reliable." "No," Knudsen countered. "I am talking about having tanks. Your perfect tank that takes 3 months to build might be superior to my tank that takes 1 month to build, but I can give you 3 tanks in the same time. Which would you prefer in North Africa right now?" The argument raged for hours. Military engineers presented legitimate concerns. Would stamped armor crack under impact? Could workers with minimal training really assemble complex transmissions? What about quality control when production accelerated? Each objection reflected decades of weapons manufacturing wisdom. According to Thomas Heinrich's historical analysis in Ships for the Seven Seas, which examined similar industrial mobilization challenges in naval production, this tension between craft tradition and mass production had plagued every major weapons program. Knudsen didn't dismiss these concerns. Instead, he proposed something radical: prototype the entire system before committing. The Chrysler Tank Arsenal would be designed from the ground up as an assembly line facility. Every station would be planned, every movement choreographed, every tool positioned. They would build the first Sherman tanks using traditional methods while simultaneously developing the assembly line process. If it failed, they could revert to conventional production. What Knudsen didn't tell them was that failure wasn't an option he accepted. He'd already recruited industrial engineers from Ford, General Motors, and Chrysler. He'd contacted suppliers about standardized components. He'd even begun designing specialized machinery, welding fixtures, plate rolling equipment, turret mounting jigs, that didn't yet exist. The generals reluctantly approved a limited trial, giving Knudsen 6 months to prove his system could work without compromising quality. He had 4 months before the Marines would desperately need tanks at Guadalcanal. Spring, 1942. The Chrysler Tank Arsenal rose from Michigan farmland with desperate urgency, its steel frame climbing skyward as welders worked around the clock. But the real innovation wasn't the building itself. It was the intricate choreography being designed within its walls. Knudsen had assembled an unusual team: automotive production engineers who'd never seen a tank, military ordnance specialists who'd never worked an assembly line, and industrial psychologists studying how to train workers for tasks that didn't yet exist. The central challenge was sequencing. Traditional tank assembly was non-linear. Different teams worked simultaneously on various components, eventually converging in a final assembly that required extensive fitting and adjustment. Knudsen needed to transform this chaos into a linear flow where each station added specific components in a predetermined order, with each tank moving continuously through the facility, like cars through a Ford plant. Edward Rushton, a former Ford production supervisor, led the floor planning team. His task seemed impossible, map every single operation required to build a Sherman tank, determine their optimal sequence, calculate precise timing for each station, and design tooling that would allow semi-skilled workers to perform tasks that currently required craftsmen. Rushton's team created a massive flowchart that covered an entire warehouse wall, tracking dozens of parallel sub-assembly lines that would feed into the main production sequence. The hull assembly illustrated the challenge. Traditional methods involved positioning armor plates on a frame, hand-drilling thousands of rivet holes to match each plate's unique position, then riveting them in place, a process taking days. Knudson's system required pre-drilling all holes in stamped plates at a separate station, using precision jigs that ensured every plate was identical. Workers at the hull station would simply position plates against standardized fixtures and rivet them in predetermined patterns. No measuring, no marking, no custom fitting. Critics called it a fantasy. Colonel Raymond Barker, assigned as military liaison to the project, watched early tests with barely concealed skepticism. "You're assuming perfect parts," he observed, as workers struggled to fit a transmission housing that was millimeters off specification. In reality, nothing is perfect. That's why skilled fitters are essential. They compensate for variation. Knudson's response was characteristically blunt. "Then we must eliminate the variation." He established quality standards more rigorous than anything in automotive production. Suppliers received specifications with tolerances measured in 10,000ths of an inch. Components that deviated were rejected entirely, not adjusted. Early rejection rates exceeded 30%, creating supplier chaos. One transmission manufacturer called Knudson's standards theoretically achievable but practically impossible. According to War Production Board documents, referenced in Arthur Herman's Freedom's Forge, Knudson personally visited struggling suppliers, bringing automotive quality control experts who taught precision manufacturing techniques. He replaced suppliers who couldn't meet specifications, even when it meant short-term production delays. The message was clear. The system required perfect parts, and nothing less would be accepted. Meanwhile, the human element presented equal challenges. Traditional tank workers were skilled craftsmen with years of metalworking experience. Knudson's system needed thousands of workers who could learn specific tasks in days, not years. Industrial psychologist Adelaide North joined the team, studying how to break complex operations into simple, repeatable motions. She developed training programs that taught single operations in isolation, then gradually introduced workers to adjacent tasks. The approach seemed dehumanizing to some observers. Workers weren't learning a trade. They were learning to perform specific limited operations. Union representatives worried about de-skilling labor, reducing proud craftsmen to interchangeable machine tenders. Knudson acknowledged the concern but remained pragmatic. "We need 10,000 workers in 6 months. We cannot train 10,000 craftsmen. We can train 10,000 specialists." By May 1942, the first Sherman tanks began moving through the prototype assembly line. They moved slowly, far slower than Knudson's projections. Bottlenecks appeared at unpredictable stations. Tooling failed. Workers struggled with sequencing. The first assembly line Sherman took nearly as long to build as a handcrafted tank, but it moved, and every day, it moved slightly faster. The real test was approaching. Could this system produce combat-ready tanks that would actually work in battle? The first 50 assembly line Sherman tanks rolled out of the Chrysler Arsenal in July 1942. Their olive-drab paint still curing as they were loaded onto railcars bound for California, then ships to the Pacific. Knudson felt no celebration, only grim awareness that his untested system was about to face the ultimate validation. If these tanks failed in combat because of production shortcuts or quality issues, his entire program would collapse. The Army would revert to traditional manufacturing, and America's tank production would remain inadequate for a two-front war. The Marines received the Shermans at Guadalcanal with desperate gratitude. They'd been fighting with M3 Stuarts, light tanks that were outgunned and under-armored against Japanese positions. The Shermans represented a massive firepower increase. But would they actually work? Tank crews examined them with suspicious eyes, comparing these mass-produced machines to the handcrafted tanks they'd trained on. Lieutenant Harold Bauer commanded one of the first Sherman platoons into combat. His after-action report, preserved in Marine Corps archives, revealed immediate problems. One tank's transmission failed after just 8 hours of operation. Another experienced turret ring jamming, the kind of issue that occurred when parts weren't properly fitted. A third developed engine problems that mechanics traced to inconsistent assembly of the cooling system. Out of 12 tanks in the initial deployment, 4 experienced mechanical failures within the first week. Back in Detroit, Knudsen received the reports with controlled fury. This was exactly what critics had predicted. Assembly line production sacrificing reliability for speed. Colonel Barker, the military liaison, didn't hide his vindication. "Perhaps now we can return to sensible production methods," he suggested at a tense morning meeting. "These failures are getting Marines killed." But Knudsen saw something different in the data. He spread the failure reports across his desk, noting details that others missed. The transmission failure was traced to a single supplier's quality control lapse, not a systemic design issue. The turret ring jamming came from improper lubrication during pre-shipment maintenance, not manufacturing defects. The engine problem was an assembly sequence error at one specific workstation that could be corrected immediately. These weren't failures of the concept, they were solvable problems in the execution. "How many tanks were operational?" Knudsen asked. 8 out of 12, Barker admitted. And how many tanks would we have sent using traditional production in the same time frame? The room fell silent. Everyone knew the answer. Possibly 3 tanks, maximum 4. Even with the failures, the assembly line system had delivered more functional combat vehicles than traditional methods could have provided. Knudsen didn't defend the failures. Instead, he implemented what became known as battle line feedback, a direct communication channel between combat units and factory floor supervisors. When a tank failed in combat, engineers in Detroit would receive detailed reports within 48 hours. They would identify the root cause, implement corrections, and track whether the issue recurred. This created an unprecedented feedback loop between battlefield performance and manufacturing process. The improvements came rapidly. The supplier with quality control problems was given 2 weeks to meet specifications or be replaced. They met the deadline. The assembly sequence causing engine issues was reorganized, with additional verification steps. Most significantly, Knudsen established a combat simulation protocol where every 10th tank would be subjected to accelerated stress testing before shipment, identifying potential failures before they reached combat zones. By August, the second wave of Shermans reached the Pacific with dramatically improved reliability. According to military logistics records, documented in R. Elberton Smith's official Army history, the Army and Economic Mobilization, operational readiness rates exceeded 80%, higher than handcrafted tanks produced through traditional methods. The assembly line Shermans weren't just adequate, they were becoming genuinely reliable. But reliability alone wouldn't win the argument. Knudsen needed to prove that his system could scale, that the Chrysler arsenal could actually produce tanks at rates that would change the strategic calculus of the war. The generals had given him a production target that still seemed impossible, 1,000 tanks per month by December 1942. As summer turned to autumn, the assembly lines accelerated. The facility that had taken weeks to produce a single tank was now completing tanks in days. Workers who had fumbled with unfamiliar tools now moved with choreographed precision. The impossible was becoming routine. But Knudsen knew the real test was still coming. Could American industry not just build tanks, but build them so rapidly that quantity itself would become a weapon? Autumn 1942. By October 1942, the Chrysler tank arsenal operated 24 hours daily across 3 shifts, and the assembly line had achieved something that would have seemed like fiction just 1 year earlier. A completed Sherman tank rolled off the line every 4 hours. Knudsen stood on the observation platform overlooking the main production floor, watching the choreographed chaos below. 600 workers moved through their specialized tasks: welding, riveting, installing, testing. Each person a precisely positioned element in a mechanical ballet. The numbers told a story that military planners were only beginning to comprehend. In September, the arsenal had produced 247 tanks. In October, 318. The trajectory was clear. By year's end, monthly production would exceed 1,000 vehicles. Meanwhile, traditional manufacturing facilities were still producing perhaps 50 tanks monthly, despite working at full capacity. Knudsen's impossible system was outproducing conventional methods by a factor of 20. But raw production numbers masked a more profound transformation. The real revolution wasn't speed, it was scalability and standardization. Because every component was interchangeable and every process was documented, Knudsen could replicate the entire system. In Pennsylvania, the Baldwin Locomotive Works was converting to tank production using Chrysler's blueprints. In Illinois, Pressed Steel Car Company was building an identical facility. Fisher Body, Ford, Pacific Car, and Foundry, industrial giants, were preparing to join the production network, each using the same standardized processes, parts, and specifications. General George Marshall, Army Chief of Staff, visited the arsenal in November. He walked the production floor with Knudsen, observing workers who'd been farmhands or retail clerks 6 months earlier, now assembling complex military vehicles. At one station, a woman named Dorothy Henson was installing periscope assemblies, a task requiring precise alignment and focus, but only 3 days of training. Marshall watched her complete 4 installations in 20 minutes, each one identical. "How many workers do you have here?" Marshall asked. "Currently 6,200, Knudsen replied. "We will add another 2,000 by January." And they're producing over 300 tanks monthly with a workforce smaller than a single battleship construction project. Marshall wasn't asking a question, he was processing the implications. Naval shipyards employed tens of thousands to produce individual vessels over years. Knudsen was producing complex armored vehicles with comparable capability, using a fraction of the labor in weeks instead of months. The strategic calculus was shifting. British and Soviet intelligence reported German tank production at approximately 500 units monthly across all factories, about half what Chrysler alone would achieve by year's end. When the other American facilities came online in 1943, total American tank production could exceed 3,000 monthly. The Germans, even with their captured European industrial base, couldn't match those numbers. According to Richard Overy's analysis in Why the Allies Won, examining comparative war production, this differential represented more than manufacturing efficiency. It was a fundamental strategic advantage. Germany fought a war of quality, producing technically sophisticated tanks like the Tiger and Panther that were superior to Shermans in direct combat, but German factories couldn't produce those superior tanks in sufficient numbers. America was pursuing a strategy of overwhelming quantity, accepting that individual Shermans might be inferior while ensuring numerical dominance. The strategy had critics within American military leadership. General Leslie McNair, head of Army Ground Forces, argued that American tanks should match German technical specifications. "We're sending our boys into battle in inferior equipment," he complained during a Pentagon briefing. "A Tiger tank can destroy 3 Shermans before being knocked out." General Dwight Eisenhower, planning the North African invasion, saw it differently. "I'd rather have 3 Shermans," he countered. "Because I'll have 3 Shermans. The Germans will have 1 Tiger, and we can't be sure it'll even reach the battlefield given their supply problems." Eisenhower understood that wars weren't won by individual vehicle performance. They were won by sustained force applied across multiple fronts simultaneously. Knudsen never entered these strategic debates directly. His focus remained relentlessly practical. Improve the process, eliminate waste, accelerate production. But he understood the deeper truth. His assembly line system had transformed tanks from precious resources to abundant commodities. American commanders could use tanks aggressively, accept losses, and no replacements would arrive within weeks. German commanders had to husband each tank carefully, knowing replacements might take months. By December 1942, the Chrysler arsenal achieved its target: 1,037 Sherman tanks completed in a single month. President Roosevelt personally called Knudsen to offer congratulations, but Knudsen barely acknowledged the achievement. He was already focused on the next challenge: accelerating production even further while reducing costs. The war was far from over, but the industrial foundation for Allied victory was being welded together on the factory floors of Detroit. Winter, 1943. The production numbers looked triumphant in War Department briefings. 4,000 tanks per month flowing from American factories by February 1943, an industrial achievement without historical precedent. But inside the Chrysler tank arsenal, William Knudsen faced a crisis that couldn't be solved with engineering diagrams or process optimization. The human cost of his assembly line system was becoming impossible to ignore. Worker injury rates had climbed steadily as production accelerated. In January 1943 alone, the arsenal recorded 147 serious injuries: crushed fingers from stamping presses, burns from welding stations, lacerations from metal edges, back injuries from repetitive lifting. The facility's medical station, designed for minor first aid, was overwhelmed. 3 workers had died in industrial accidents since production began, their deaths investigated by Army safety inspectors who found that speed pressures contributed to inadequate safety protocols. Catherine Wells, a labor organizer with the United Auto Workers, confronted Knudsen in his office one February morning. She brought photographs: workers with bandaged hands, a young man on crutches after a loading accident, documentation of 12-hour shifts with minimal breaks. "You're sacrificing these people to your production schedules," she accused. "They're not machine parts that can be replaced when they break." Knudsen didn't deflect or defend. He'd visited injured workers in hospitals, seen the exhaustion in their eyes during shift changes. The relentless drive for production had created dangerous shortcuts: safety guards removed to speed operations, maintenance deferred to avoid production downtime, workers pushed beyond reasonable fatigue limits. His system treated efficiency as the paramount value, and people were paying the price. "What do you propose?" he asked Wells. She presented demands: mandatory safety protocols even if they slowed production, regular breaks, injury compensation, reduction in shift length from 12 hours to 10. Each demand would reduce output. Knudsen calculated quickly. Implementing these changes might reduce monthly production by 15%. That meant 600 fewer tanks monthly, potentially affecting military operations in North Africa or the planned invasion of Italy. The moral arithmetic was brutal. More safety meant fewer tanks, which might mean more soldiers dying because they lacked armored support. Fewer safety regulations meant more worker injuries, but more equipment for the front lines. Neither choice was acceptable, yet a choice had to be made. Knudsen visited the factory floor that night, walking through the third shift when exhaustion was most visible. He watched a young woman named Alice Porter operating a turret-mounting crane, her movements mechanical after 9 hours on shift. He saw the safety violation immediately. She'd removed her protective gloves because they made the controls harder to grip. One mistake, one moment of fatigue, and she could lose fingers or worse. This was happening throughout the facility, invisible shortcuts taken by exhausted workers trying to meet production quotas. The next morning, Knudsen did something that shocked the War Department. He ordered production reduced by 20% while safety systems were completely overhauled. Every dangerous operation was halted, analyzed, and redesigned with worker protection as primary consideration. Safety guards were redesigned to be less obtrusive but impossible to bypass. Shift lengths were reduced. Mandatory rest periods were enforced. The arsenal hired 50 additional safety supervisors whose sole job was preventing injuries, even if it meant stopping production. General Devers called personally. "You're cutting tank production during active military operations. Do you understand what you're doing?" "I understand that injured workers cannot produce tanks," Knudsen replied. "I understand that exhausted workers make mistakes that cause quality problems. And I understand that we cannot win this war by destroying the people building our weapons." The production statistics for March 1943 showed the impact: 841 tanks instead of the projected 1,000. War Department officials were furious. Some called for Knudsen's replacement. But by April, something unexpected happened. Production recovered to 963 tanks, approaching previous levels despite shorter shifts and stricter safety protocols. Worker injury rates dropped by 40%. Quality defect rates decreased noticeably. According to labor studies conducted by the War Manpower Commission, documented in Amy Kesselman's Fleeting Opportunities, Knudsen's arsenal became a model for sustainable wartime production. Workers who felt protected and valued were more productive, not less. The injury reduction eliminated production disruptions caused by worker replacement and training. Better rested workers made fewer errors, reducing quality control failures and rework. The lesson extended beyond simple humanitarianism. Knudsen realized that his original system had been incomplete. It had optimized for mechanical efficiency while treating human workers as infinitely replaceable components. The revised system acknowledged that people weren't machines, that sustainable production required protecting the workforce as carefully as maintaining the machinery. By summer 1943, other war production facilities began adopting the arsenal's safety protocols. The system Knudsen had pioneered was evolving beyond pure efficiency toward something more complex, an industrial model that balanced production demands with human welfare. But even as the domestic production system matured, the global strategic situation was creating new challenges that would test whether Knudsen's industrial revolution could adapt to changing battlefield requirements. Summer 1943. Through winter 1944. The telegram from General Omar Bradley arrived at Knudsen's office in July 1943, marked urgent. Sherman inadequate against new German armor. Require immediate design modifications. Cannot wait for traditional development cycle. The message confirmed Knudsen's worst fear. Battlefield requirements were changing faster than his production system could adapt. The Germans had deployed heavier tanks with thicker armor and more powerful guns. American Shermans, designed for mass production in 1941, were becoming obsolete. Traditional military procurement would have required years to design, test, and produce an entirely new tank. The Army's Ordnance Department had already begun work on the M26 Pershing, a heavy tank designed to match German Tigers, but the Pershing wouldn't enter production until late 1944 at the earliest. Bradley needed solutions immediately, and Knudsen's assembly line system seemed to be the very obstacle preventing rapid adaptation. Or was it? Knudsen assembled his engineering team with a radical question. Could they modify the Sherman significantly without disrupting production? Every engineer in the room understood the problem. Assembly line manufacturing depended on standardization, identical components, fixed sequences, specialized tooling. Major design changes meant retooling entire production lines, retraining workers, establishing new supplier specifications. The conventional wisdom was clear. You couldn't have both mass production and rapid design evolution. Joseph Colby, the Arsenal's chief design engineer, proposed something unprecedented. Modular upgrades that could be integrated into existing production without stopping assembly lines. Rather than redesigning the entire tank, they would create improved components that were dimensionally compatible with existing systems. Thicker frontal armor plates using the same mounting points, upgraded guns that fit existing turret configurations, enhanced suspension components that could be swapped with minimal retooling. The approach required thinking about the Sherman not as a fixed design, but as a platform, a standardized structure that could accept multiple configurations. Each modification would be tested individually, then gradually integrated into production. At any given time, the assembly line might be producing several Sherman variants simultaneously, each incorporating different combinations of upgrades. Implementation proved extraordinarily complex. Consider the armor upgrade. Engineers designed applique plates, additional armor welded onto existing hulls, that could be added at a dedicated station inserted into the production sequence. Tanks destined for the European theater, where they'd face heavy German armor, received the upgrade. Tanks for the Pacific, where Japanese anti-tank weapons were less formidable, continued with standard armor. The same assembly line was now producing differentiated products. By September 1943, the Arsenal was manufacturing 4 distinct Sherman variants simultaneously, each optimized for different combat scenarios. The M4A3 with a more powerful gun and improved armor. The M4A4 with revised suspension for European terrain. The M4A3E8 with wider tracks for better mobility. And the standard M4 for situations where basic capability was sufficient. Production complexity increased enormously, but the system absorbed it. According to military logistics records, referenced in Stephen Zaloga's comprehensive Armored Thunderbolt, This production flexibility gave American forces an unprecedented advantage. When intelligence revealed German tank deployments in specific sectors, American commanders could request Sherman variants optimized for those threats. Units in Italy received tanks with improved hill climbing capability. Forces in France got tanks with enhanced frontal armor. Pacific units received standard versions where weight savings improved strategic mobility. The Germans, despite their technical sophistication, couldn't match this adaptability. Their superior tanks required specialized production facilities and highly skilled labor. Each design change meant months of retooling. They couldn't rapidly respond to battlefield feedback because their craft-based manufacturing system wasn't designed for quick iteration. But Knudsen's system had a hidden vulnerability that became apparent in late 1943. Complexity was creating new quality control challenges. With multiple variants moving through the same production lines, workers had to identify which configuration they were building and apply appropriate components. Mistakes were inevitable. In December, inspectors discovered that 73 tanks had been shipped with incorrect armor specifications, a quality control failure that could have been catastrophic in combat. Knudsen responded by implementing color coding systems and enhanced documentation that traveled with each tank through production. Every vehicle received a specification card indicating its configuration. Each workstation had visual guides showing component differences between variants. The system evolved from simple standardization toward managed complexity, maintaining production speed while handling unprecedented variation. By early 1944, as Allied forces prepared for the Normandy invasion, American factories were producing over 5,000 tanks monthly in multiple configurations. The assembly line system that critics had called inflexible had proven more adaptable than traditional manufacturing methods. Knudsen had created something unique in industrial history: mass production with custom variation, combining the efficiency of standardization with the responsiveness of craft production. But the ultimate test was approaching: the invasion of Europe, where his tanks would face the German war machine in battles that would determine civilization's future. Spring 1944. Through victory. When Allied forces stormed the Normandy beaches on June 6, 1944, more than 2,000 Sherman tanks supported the invasion, a concentration of armored force that would have been unthinkable just 3 years earlier. General Dwight Eisenhower stood on the English coast watching waves of landing craft approach the French shore, knowing that Knudsen's production system had made this moment possible. The operation's success didn't depend on having the best tanks. It depended on having enough tanks to overwhelm German defenses through sheer numerical superiority. The brutal mathematics of the European campaign validated Knudsen's fundamental insight. German Tiger and Panther tanks were individually superior to Sherman's: more armor, bigger guns, better battlefield performance. But American production had achieved a staggering 5-to-1 numerical advantage. For every German tank produced, 5 Shermans rolled off American assembly lines. Allied commanders could afford to lose 2 or 3 Shermans destroying a single German tank and still maintain operational superiority. Captain James Bates, commanding a Sherman platoon in the 1st Armored Division, wrote home in July 1944, describing the reality: "We lost 2 tanks today to a single Panther, but we knocked it out, and tomorrow we'll have replacement tanks. The Germans won't. That's how we're winning this. Not by having better equipment, but by having more of it than they can possibly destroy." The production numbers told the story. From 1942 through 1945, American factories produced approximately 49,000 medium tanks, primarily Shermans. Germany produced roughly 24,000 tanks total across all types during the same period. The Soviet Union, using similar mass production principles, produced 57,000 T-34 tanks. The Axis powers were being buried under an avalanche of armor they couldn't match. But Knudsen never celebrated the achievement. He visited Veterans Administration hospitals in late 1944, talking with tank crews who'd been wounded in combat. Some described watching better German tanks destroy their Shermans before being overwhelmed by numbers. The moral complexity haunted him. Had his production system saved lives by providing overwhelming force, or had it condemned soldiers to fight in inferior equipment because superior designs couldn't be mass-produced? General George Patton, whose Third Army drove across France with Sherman-based armored divisions, offered his characteristic bluntness in a 1945 interview. "The Sherman is a good tank. Not great, but good. And we've got so damned many of them that it doesn't matter. I can lose a dozen tanks taking an objective and have them replaced within a week. The Germans can't do that, so they have to be cautious. We can be aggressive. That's the difference between winning and losing." The final production statistics, compiled by the War Production Board after Germany's surrender in May 1945, revealed the scale of Knudsen's industrial revolution. The Chrysler tank arsenal alone had produced 25,000 tanks. Across all facilities using his system, total production exceeded 70,000 armored vehicles, including variants and support vehicles. The impossible blueprint had not only succeeded, it had transformed industrial warfare itself. William Knudsen received the Army Distinguished Service Medal in a quiet Pentagon ceremony in September 1945. President Truman personally thanked him for service that turned American industrial might into the arsenal of democracy. But Knudsen's speech at the ceremony was characteristically modest. "We simply applied sound engineering principles to manufacturing problems. The credit belongs to tens of thousands of workers who built these tanks, and to the soldiers who used them to defeat tyranny." The historical verdict on Knudsen's achievement has evolved over decades. Military historians debate whether American tank design should have prioritized quality over quantity. Industrial historians study his methods as foundational to modern manufacturing. Labor historians examine both the innovations and exploitations of his production system. The truth contains elements of all these perspectives. What remains indisputable is that Knudsen's impossible blueprint changed how nations think about industrial mobilization. He proved that with proper engineering, even complex weapon systems could be mass-produced. He demonstrated that standardization and flexibility weren't contradictory. They could be integrated through thoughtful system design. Most significantly, he showed that production itself could be a strategic weapon, that overwhelming quantity could compensate for individual product limitations. When William Knudsen died in April 1948 at the age of 69, his obituaries focused on his automotive career, the man who'd helped build General Motors into an industrial giant. Few mentioned that his greatest contribution wasn't building cars for peacetime prosperity, but transforming how democracies could mobilize industrial power against totalitarian threats. The assembly line tank production system he pioneered became the template for Cold War military manufacturing. When America needed aircraft carriers, jet fighters, or nuclear submarines, planners studied Knudsen's methods: standardization, interchangeable components, continuous improvement, modular design. The principles he'd fought to implement against skeptical generals became orthodox doctrine taught at military academies and business schools worldwide. Yet the deeper legacy remained ambiguous. Post-war analysis by the Strategic Bombing Survey revealed that German tank crews genuinely feared Shermans, not because of their combat capabilities, but because of their inexhaustibility. A German panzer commander interviewed in 1946 described the psychological impact. "We could destroy 5, 10, even 15 enemy tanks, but more always came. Eventually you realized that destroying enemy tanks was meaningless. They had infinite tanks. We did not." This psychological dimension, the demoralization of facing an enemy with seemingly unlimited resources, was perhaps Knudsen's most profound contribution. He hadn't just solved a production problem, he'd weaponized American industrial capacity itself, turning factories into instruments of strategic despair for adversaries who couldn't match the output. The workers who'd built those tanks scattered after the war. Dorothy Henson, the periscope installer General Marshall had observed, returned to teaching. Alice Porter, whose near injury had catalyzed Knudsen's safety reforms, became a union organizer fighting for industrial worker protections. Thousands of women who'd learned precision manufacturing were pushed out of factories as male veterans reclaimed jobs, their contributions often forgotten in official histories. In 1947, Knudsen gave his final public speech at the Society of Automotive Engineers. He was frail, his health declining, but his message carried the weight of hard-earned wisdom. "We learned that impossible is merely difficult that hasn't been properly analyzed. We learned that people, not machines, are the heart of production. We learned that speed without quality is waste, but quality without speed is luxury we cannot always afford. Most importantly, we learned that free societies, when truly threatened, can mobilize industrial power that tyrannies cannot match. He paused, looking out at an audience of engineers who'd helped win the war, then added something rarely acknowledged. But we must also remember the cost. Every tank we built represented resources not used for schools, hospitals, homes. Every worker we pushed to exhaustion was someone's parent, spouse, child. Victory required these sacrifices, but we must never glorify them. Industrial mobilization is a terrible necessity, not an ideal to pursue. The Chrysler tank arsenal continued operating through the Korean War, producing M46 and M47 Patton tanks using evolved versions of Knudson's systems. It finally closed in 1996, its massive assembly halls eventually demolished. A small historical marker now stands where tanks once rolled off assembly lines at rates that had seemed impossible, commemorating a place where American industrial might achieved something unprecedented. Today, in an era of precision-guided weapons and advanced manufacturing technologies, Knudson's achievement can seem quaint, a relic of industrial warfare that modern militaries have surpassed. But defense planners studying potential great power conflicts increasingly reference his work, recognizing that sustained warfare still requires industrial capacity to replace losses and maintain force levels. The specific technologies have evolved, but the fundamental challenge Knudson addressed remains relevant. How do you rapidly produce complex systems in quantities that matter strategically? Perhaps the most fitting tribute came not from military leaders or fellow engineers, but from a former tank crewman named Robert Morrison, who'd fought from Normandy to Germany. In a 1985 interview, Morrison reflected on his war experience. "I never met Mr. Knudson, never even saw his picture during the war, but I thought about him every time we got replacement tanks after a battle. Some engineer back in Detroit figured out how to keep us supplied with the tools we needed. That mattered more than any individual tank's capability. He helped us win by making sure we never ran out of tanks, no matter how many we lost." That simple statement captured the essence of Knudson's achievement. He hadn't built the best tank. He'd built a system that ensured soldiers would always have tanks. Enough tanks to overwhelm enemies, replace losses, maintain pressure, and ultimately prevail through sustained force that adversaries couldn't match. The blueprint that military experts had called impossible in 1941 had proven to be not just possible, but transformative. William Knudson had taken the assembly line principles that made affordable automobiles available to millions and adapted them to the most challenging manufacturing problem of the 20th century. In doing so, he'd helped demonstrate that industrial democracies, despite appearing chaotic and inefficient compared to centralized totalitarian states, possessed latent capabilities that authoritarian systems couldn't replicate. The tanks that rolled off his assembly lines like cars had carried more than soldiers and ammunition. They'd carried proof that free societies, when existentially threatened, could organize themselves with efficiency that matched or exceeded any dictatorship. That profound demonstration of democratic industrial power, not just the specific production numbers or engineering innovations, became Knudson's enduring legacy, a reminder that seemingly impossible challenges often yield to persistent engineering, human ingenuity, and the organized effort of free people defending their civilization. The impossible had become routine, and in becoming routine it had helped save the world.